Okay. All right. So what we want to do though is we want to, like, what's your name? Raji. Okay. Raji. We want to figure out how to evaluate limits algebraically. That's like where we're headed, so that we can use it in our calculus. And that's one of the more useful things. So what we need to do though, we need to talk about continuity. Now, you probably have a pretty good intuitive sense of what it means to be continuous, for a function to be continuous. Basically, I mean, kind of the traditional way of looking at it is if you can graph a function without lifting your pencil, then it's continuous. Okay, now this function that I just drew, would I be able to graph this without lifting my pencil? No. Okay. Now the problem with that is that it's not entirely accurate, and because the kinds of functions that we work with in calculus are more and more complicated, we need to be much more specific about what it means for a function to be continuous. So let's write down so this is going to be my example function here. So this is f. So it looks pretty similar to the one we had earlier. So let's see. Let me do, okay. So we have definition. So a function f is continuous at x equals a if and only if the limit as x approaches a of f of x equals to f of a. Okay, and that's it. So that's the definition of continuity. So what do we have? We have basically two things. We have the limit of the function, and we have, what's f of a? That is the value of the function, right? Basically the y value if you're looking at the graph. So this, the right side is the y value. Compare that to the limit, right? And if those two things are equal, then you say that the function is continuous at that point, right? So that seems pretty pretty easy. Let's see. If it is not continuous, then how would you call that? Take a wild guess. We say it is discontinuous. Okay, good. Move my page down a bit here. We say it is discontinuous. Okay. At x equals a, let's say. All right, now there are multiple types of discontinuities. So, types of discontinuities. There are three types. They're all right here in this picture that I just drew for you guys. Types of disco. See, my board doesn't go any further. I'll buy a bigger board next time. Promise. Okay, types of discontinuity. Discontinuities. All right, one. No, wait. Let me do this. Let me color code it. Let's see. Let's see about purple. Okay, so this will be easy to identify. Jump. So what does a jump discontinuity look like? Well, if the limit as x approaches a from the left does not equal to the limit as x approaches a from the right. So that, in that case, you have a jump discontinuity. So which one is the, well, let me mark here the three kind of key points here on our graphs. Let's label this, what should I label this? Maybe x1, x2, and x3. Is that all right? Kind of the 3 points where the stuff is happening, right? Okay, so which one? Where's their jump discontinuity? Just by the name. X1, right? So notice the limit as x approaches x1 from the left is different than if you approach it from the right, so you have a jump discontinuity. So that one's pretty easy to figure out there. So that is, so this is jump, right? All right, the second type is called removable. And it's called removable because you can remove the discontinuity by just changing 1 point. So take a wild guess, which one's that? X2, right? If you fill in the hole, then you got rid of the discontinuity. Whereas this, you would have to change a bunch of points to kind of connect the two. Does that make sense? So this is if the limit as x approaches a of f of x exists. So if the limit exists, but it is not equal to the value of the function at the point. Okay, so do you guys agree that at x2 the limit exists but is not equal to the value of the function? Do you guys agree with that? What is the value of the function? Doesn't exist, right? What's the limit? Whatever that number is, right? We didn't really label it, but the limit exists. It's some number. Do you guys agree? Okay, now let me just change the graph one tiny bit just to ask you if, okay, is that still a removable discontinuity based on the definition?
No. Yes.
Yes. Good. Yes, it is. Because notice the limit still exists, right? What's the value of the function in this case? Yeah, whatever y value that is, right? So it equals to something, but is it the same as the limit? No. Right? So the limit exists, the function exists, but they're not the same. So then it's removable. Does that make sense? Okay. And notice you can still remove the discontinuity by just changing 1 point. You take that dot and put it up there, stick it in the hole, right? Then plug up the hole. Yes, okay. Okay. All right. Last one. Take a wild guess. What do you guys think it's called? The third one. Infinite. Infinite. That's an excellent choice. That is exactly what it's called. How did you guys know? You guys have been paying attention. So I had to write it down here because I didn't do a good job. Infinite discontinuity. So this is if the limit as x approaches a from the right or the left, f of x, is equal to positive or negative infinity. So basically, if you have a vertical asymptote, then it's an infinite. So here, this one, x3, is a... Okay. All right. Does that make sense?
Is that either side or both, the infinite?
Yeah. Either side or both. All right. So that makes sense, right? So let's do an example here. So this. Okay. All right. Let's say we have. Let's see here. All right. Example. All right, so let's do a fun function. How about that? F of x equals to x squared minus 2 if x is less than 2. Let's say x, let's see, 2, let's say 4x minus, wait, what is that? Oh, 6. Let's do that. 6. If x is between 2 and, oh, I don't know. How about pi? Just to throw in some fun stuff here. And then how about, let's do cotangent of x over 2 when x is, oh, less than, yeah, shoot. Okay, hold on. I'll fix it. I'll fix it. Let's see. If x is less than pi, and then if x is greater than or equal to pi. How about that? All right. Okay, so I'm going to give you guys a few minutes. You want to, what do you want to do? You want to find all discontinuities and their type. Can you guys do that? Or should we do this one together and then I'll give you guys another one? How do you guys feel? Do you guys feel like you want to get? Yeah, you guys think it'll work. Okay. All right, go ahead. Give it a go. Why don't you guys get into buddies? You know, strengthen numbers. So you can, you know, get buddy up with your neighbor there, and you guys can work on it together. Okay, so let's see. Let's try to draw a rough sketch here. Because so far, all we know how to do is evaluate limits by graphing. Do you guys agree with that assessment? Okay, so let's say this is 1, 2, 3, 4, minus 1. Okay, so let's see. Let's do green for this one. So x squared minus 2. So we don't need to have an absolute perfect graph. We just need to know roughly what this looks like. So what is this? This is a parabola shifted down 2, right? Okay, so parabola shifted down 2. What does it equal at x equals 2? 2. Okay, so let's do that so that we at least have that point accurate.
It's an open circle. Open circle at 2.
Circle for that portion of the piece.
Right, so at 2 there's an open circle. Yes?
Yes.
Okay. What's the x-intercept? Well, because it's shifted down 2, right? So let me do that. So minus 2 like that. And then, okay. So what is it again? So here's the vertex, right? So x-intercept is at root 2 minus root 2, kind of like that, right? Okay. That's it. So it doesn't need to be perfect, doesn't need to be wonderful. But you should know how to graph basic functions. So here, 4x minus 6. So what is that? That's a line, right? A line with a slope of 4, y-intercept of negative 6. But it's only defined between 2 and pi, right? So we need to kind of pick our points wisely. Because there's no point in doing the slope-intercept form if, you know, the y-intercept is over here, but my line isn't defined until 2. So To graph a line, it's easy, right? You just need 2 points. What would be two good x values to use?
2 and 3.
2 and 3, right? Because 3 is still less than pi, so then that's a good number. Okay. So what is it equal to at, if I plug in 2 here, what would I get?
It's all in 2.
2. Okay. So notice it overlaps there. And then if I plug in 3, what would I get? 6. So let's say 6 is right here. I totally made that up, but that's okay. And it looks like that. That, and then where's pi? Okay, so let's say pi is right there. I think this is the color. So at pi, I've got an open circle, so it looks like that, right? Does that make sense?
Yeah.
Okay, good. All right, now cotangent.
0.
Cotangent. Well, yeah, let's start at evaluating at pi. So what is cotangent of pi over 2? Well, what is the definition of
0
cotangent?
over 1.
Well, what? But yeah, what's yeah?
Cos over sine.
Yeah, cotangent is cosine over sine, right? So it's basically if you're just evaluating it at the end point, it's basically cosine of pi over 2 divided by sine of pi over 2, right? Which is 0. Yeah. Okay. So that's good. Now, so let me see. Let me pick a color. How about this orange one? Can you guys see that okay, that color? Okay. So it's equal to 0 at pi. Now, what else do you know about the cotangent, the graph of cotangent?
It's greater than pi. That one is greater
It has
than pi.
vertical
And it goes
asymptote.
positive to negative.
It has vertical asymptotes, right? How many vertical asymptotes? Infinitely many, right? Okay, so kind of, why don't we do this on the side? This is a good review of your trig stuff. How many of you guys were able to make it to the trig review, by the way? Nobody? Really?
We all have jobs.
At class. That's why we come late.
Nobody was able to make it to the trig. All right, well, you guys need to review your trig. But, okay, so cotangent of x over 2. Okay, so this is just kind of, you know, just like a really, really quick refresher on what the basic cotangent graph looks like. If I graph cotangent of x, it has a period of what? Pi. Where is the first vertical asymptote? If you're starting at 0,
That's 0. That's pi.
0, there's a vertical asymptote at 0, right? Because sine of 0 is 0, so there's a vertical asymptote there. Where's the next vertical asymptote? At pi, right? Does that make sense? So the cotangent graph looks like this. So it has a vertical asymptote here, vertical asymptote here, vertical asymptote here, right? And I mean, if I'm just kind of graphing it, just kind of looks like that, right? And it just keeps repeating itself. Now, so normally these are 0 and pi. Now because I have x divided by 2, what does that do to the period? Doubles it, right? So now instead of being at 0, pi, 2 pi, 3 pi, it's going to be 0, 2 pi, 4 pi. Yep. Okay, so this is vertical asymptote at 0, 2 pi, another one at 4 pi, and so on. Okay, all right. So here's pi. So if I'm kind of matching up the points here, this pi right here, where it's 0, right there, where is that over here? Well, that's right there, right? Does that make sense? Right there. So let's see here. So somewhere over here, I'm going to have a vertical asymptote, 2 pi, and my cotangent graph looks like this, right? Okay. Now, is that the end of my function? Did I completely graph my function? No. What am I missing? the rest of cotangent of x over 2, right? Because cotangent of x over 2 is defined when x is greater than or equal to pi. So I need to keep graphing cotangent of x over 2. So this keeps going. So here I have this, and this is, where's this? 4 pi. Okay. And, all right. So, so here's the graph. So we have pretty much graphed the function here. Did a pretty good job. Now let's write down the, let me leave it up here like that. Okay. Let me erase this stuff, and then we'll write down the discontinuities. So, let's see. All right, so what do you say? So it's discontinuous. So is it discontinuous at 2? It isn't, right? So notice, even though the function definition changes at x equals 2, because they match up at the same y value, then it is continuous, right? Because what's the limit as x approaches 2 from the left and from the right? 2. What's the value of the function at 2? 2. Exactly. So we'll maybe make a note. F is continuous at x equals 2 since the limit as x approaches 2 of f of x equals to 2, which equals to I have a space here a little bit, which equals to f of 2. And that's the requirement, right? To be continuous, the limit has to equal to the value of the function at the point. Done. Does that make sense? Okay, good. All right. Now, what about, let's see, what's the other one? Pi. What do you guys think about pi?
Jump.
There's a jump discontinuity, right? Notice the limit from the left and the right is different. Does that make sense? So we have a jump discontinuity. So we can see that from the graph, but we need to make sure that we know the definition. So why is it that it's a jump again? You guys remember? It's a jump if if they don't equal to each other, exactly. So the limit from the left equals to, this is equal to 6, right? But that doesn't equal to, wasn't it 6 or no?
No.
No, it's like 6 point something.
Oh, yeah, that's right, because it was, it would be, yeah, 4 pi minus, so this is equal to 4, from the left it's 4 pi minus 3. Wait, minus 3 or 6? Oh, shoot. Messing up all over the place. Okay. Right? Isn't it 4 pi minus 6?
Yeah.
Right.
Yeah, because we plug it. So here, so that's the y value that we're approaching. Even though we don't actually get there, that's the y value that we're approaching. Does that make sense? Yeah? Sure? Okay. You guys are looking at me funny there for a minute. Okay, now what about from the right? So this is not equal to the limit as x approaches pi from the right, which was, what was it again?
Cotangent pi over 2.
Which was 0, right?
0.
Yes.
That's what we got from the right. So if we approach from the right, we're approaching 0. Does that make sense?
Yeah.
Okay, so because it's different from the left and the right, that means it's a jump discontinuity. Okay. All right, now the next one is easy to see, but not as easy to write down. So let's do that. Because how many infinite discontinuities do I have? Infinitely many, right? So I have infinitely many infinite discontinuities. Okay, so how in the world am I going to write down that? Okay, so let's talk about this here so that I have infinite discontinuities at x equals 2. The first one was at 2 pi, right?
Right.
4 pi? 6 pi? Comma, dot, 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 right? So this is one way of writing them down. But it's very important because often we'll have to work with these. So another way to write this is we can say x is equal to, notice, look at the pattern. What do you notice? What is it? They all have pi's, and it's all of the,
2k pi.
yeah, it's all the evens, right? So how would you write that? You would say, okay, that would be 2k pi, where k is any integer greater than 0, right? Notice not any integer, because integers are positive or negative. Can it be 0? No, because if it's 0, then you're saying that there's a vertical asymptote at x equals 0. Is there a vertical asymptote at x equals 0? No, it starts at 2 pi. So so k has to be 1, 2, 3, 4, 5, right? Okay. So let's see. So k, you can write it in words. K is an integer greater than 1, but since we're learning here, might as well. What's that? Looks like a funny looking z. What does that mean? It's an integer. Yep. So you know how the real numbers, so the one you're more used to is the real numbers, right? You have that funny looking R with the 2 bars, and then you kind of, so that's real numbers. So these are all the integers. But again, I don't want all of them, right? So I have to specify where k is greater than or equal to 1. So it's an integer, but has to be greater than or equal to 1. So you can say greater than 0 if you want. So does that make sense? How this? So then if k is 1, 2, 3, 4, then 2k pi is 2 pi, 4 pi, 6 pi, and so on. Thumbs up? All right? Yeah? Okay, so questions. questions.
I got one going back to
Yes.
the floor function.
Which one? The floor function?
Yeah,
Okay.
or the greatest integer function expressed
Yes.
the floor. If you were to say express that in the ceiling, would everything be inverse?
Yeah, so the ceiling is, it's similar. So, but you would basically go to the next integer. So like the ceiling of 1.5 is 2. The ceiling of 2.1 is 3.
Right. And then it'd be okay.
Yeah. Yeah, so floor and ceiling is something you use it a lot in mainly computer science. A lot. Floors and ceilings. Any other questions? Yes.
On video, I saw checking point instead of graphing. For example, we can check points 2 pi instead of graphing.
Excellent question. Yes, now we can. Okay, so it's like you always know what I'm going to say. Okay, all right. All right. So here, check this out. Let me see. Where did my definition go? Oh, I lost it. I erased it. Okay, well, there it is right here. Right here. Okay, what is... Well, I erased it there, but... All right, right here's the key. Right there. What does that say? if the limit as x approaches a of f of x equals to f of a, then what does that mean? The function is continuous, right? Okay, so right there, this is a big, big, big deal. Because what does this tell us? This tells us that we can evaluate limits algebraically when? As long as the function is continuous, right? So if I have a function that's continuous and I'm asked, oh, find the limit. So like right now, so here, let me give you a really easy example. Okay, example. Find the limit as x approaches 2 of 4x plus 1. What does that equal to? Well, at the beginning of the day, we were given this. Well, okay, well, let's graph it, right? Take a look, go approach 2 from the right, approach 2 from the left, and so on, right? But really, what kind of function is this? It's a linear function, right? It's a line. So are lines continuous? Yes. For what values are lines continuous? All x values, right? So all real numbers. So what does that mean? What does this tell you up here with the definition of continuity? That means that you can simply plug in the x value and that'll give you the limit because they're the same because it's continuous. Does that make sense? So that's kind of the big jump here that we can say, oh, well, yeah, I know the limit. Easy peasy, lemon squeezy. What is that? 9. Bam, done. Easy. Does that make sense? Okay, now, but what's the problem? What is the problem?
Not always easy.
Not all functions are continuous at all points, right? This is an obvious problem. Well, so how are we going to sidestep this? So this is kind of looking ahead a little bit, but might as well. So let's say, for example, so let's take a look at another function. Let's say we're going to find the limit as x approaches, say, 1 of, let's say, x squared minus x over x minus 1, for example. Okay, now again, we could graph it, take a look, left and right and all that stuff, right? But so the reason why we're going through all this continuity stuff is we want to move away from having to graph it and look and, oh yeah, it looks like it, because even sometimes when you look at it, you can't really tell what's going on, right? We saw those examples where you have the oscillating thing that's all crazy, or you graph it and you can't tell there's a hole there, but there really is, that kind of thing. So for example here, is this function continuous at 1? No. So then I can't plug it in, right? Okay, so what we do, so this is kind of like, so imagine this is like a preview into next week, I guess. Because we haven't quite shown that we can do this. But I think you guys will agree that it makes sense, so I'll take the jump. So we can factor this. You guys agree?
Yes.
Okay. All right, so now this factors, right? Now I'm not going to, oh, don't like it when this happens. Look.
Oh, you have a hole.
I have a hole in my board. My board won't go to the right anymore. Oh.
You can still factor that, can't you?
Okay, so so here's the deal. So we need to be a little bit careful, but basically we can't really cancel necessarily because then it's not exactly the same function. But let me do something here that we'll talk about next time. So basically, you can break this up into when you have the product or a quotient or a sum or a difference of functions. You can break up the limits. So they're called the limit laws. So we'll see them on Monday, so we don't have enough time today. But we can break this up into the limit as x approaches 1 of x times the limit as x approaches 1 of x minus 1 over x minus 1. Okay, so do you trust me that this is a limit law and we can break up this into that?
Yes.
'Cause they're basically, I mean, so if you look at x times x minus 1 over x minus 1, you can, so I guess before, I mean, so I just want to make sure. You guys all agree that this is equal to this, right?
Yeah.
There's no doubt in our minds that these two are equal to each other?
Yeah.
Okay, all right, just make sure. Multiply straight across, right? All right. Okay, now, take a look at these separately. Okay, so this is the key right here. And we'll talk more about this next time. But what is this limit right here? Is that a continuous function? Yes, that's continuous, right? It's just x. What's the limit as x approaches 1 of x? 1. You just plug it in, right? Okay, all right, now, so this is the number 1. All right, now, what's the deal here with this other guy? Well, this, notice that, so you're finding the limit as x approaches 1. Does that mean that x is ever equal to 1? No. X never equals 1, right? When you're evaluating the limit as x approaches a number, you never actually hit the number, right? You just get closer and closer and closer to it, but you never actually hit it, right? Okay.
Like the friends of.
So imagine. So imagine x is getting closer and closer to 1. So like 0.9, 0.999, 0.9999999, 0.9999999, whatever, right? Okay. What do you notice happens when you divide x minus 1 over x minus 1? What do you always get every single time?
1.
The number 1. Why? It's exactly the same number, right? When you divide a number by itself, as long, what's the only issue you would have here? If you plugged in the number 1. Do you ever plug in the number 1? No, because it's. Does that make sense? Yeah. So here, this is always equal to 1. So then, what's the limit?
1.
Yeah, the limit equals to 1. So that's kind of the overall strategy to evaluate algebraically. Now that we have the continuity stuff combined with the limit laws, which we'll see on Monday, and then you put them together, basically allows you to evaluate almost any limit algebraically. Yes, Daniel.
So basically that last one, when you ask us to pick the limit as x approaches 1 over x minus 1 over x minus 1, we're pretty much calculating both sides, right? We're approaching from the left and we're approaching from the right. We're not really just one of them.
Yeah, in this case, we didn't really have to worry about it because what are the functions that you're looking at? You're looking at, in this case, the function x, which is continuous, and because it's continuous, then the limit from the left or the right is the same, and it also equals to the value of the function. So we have several kinds of functions that we know are continuous. For example, lines, right? What's another function type you know are continuous? Parabolas. Even more general than that. Lumping them all together. So lines, parabolas, cubics, what are those called? Lines, parabolas, cubics. What are those, if you throw them all in? So it's the P ends with an S? Polynomials, right? All polynomials are continuous, right? Squiggles. Okay, so all polynomials are continuous for all real numbers, right? What else? What other kinds of functions do you have?
Discontinuities. Piecewise.
No, think of just kind of basic function types that you have seen from previous Cal. You have the absolute value function, sure. This is defined for all real numbers. Continuous for all real numbers. You have the square root function, which is defined, or sorry, it's continuous.
Inverse.
It's continuous everywhere in its domain, right? Okay. What about rational functions? Are they continuous?
No.
Everywhere except where they have the asymptotes, right? So, but they're continuous on their domain, right? Right, because the domain takes out you take out the vertical asymptote when you find the domain. What about logs? They're continuous on their domain, right? What else? Exponentials.
On the domain.
Exponentials are continuous for all real numbers, right? On their domain if they have weird things. The trig functions, right? You have sine and cosine are continuous for all real numbers. Tangent
is not.
continuous on its domain, right? You take out all the vertical asymptotes. So you have these basic function types that you know where they are continuous, and you use that to evaluate the limits with the limit loss. Kind of put that together. Does that make sense?
Square roots are not continuous because we couldn't
On
find
their domain though. So
on the
yeah. So x greater than 0, then it's continuous. What else? What else? Any other questions? No? Is it good? Okay. Let's see. Yeah.
You said almost all of them algebraically. What do you mean?
Well, there's some, like for example, okay, so good question. Almost all of them. Let's say, for example, this one. We saw it already earlier. We know what it is because we saw the graph. But for example, this guy. What kind of algebra shenanigans can you do to change things around there? Can you like factor? Can you rationalize? Can you? No, right? It's just sine of x over x. What do you do? So we actually will see something that we can do, but it involves using some calculus type stuff. So that's why I said almost. Is that it's not, you can't just take any function and do some algebra and then figure it out. It kind of depends a little bit on the function type. So